Okay, so good morning. It is a pleasure to have with us today Professor Luciano Campi, who is Associate Professor at the London School of Economics. His research focuses on probability and stochastic processes with applications to finance. And he has recently been working on stochastic differential games and mean field games. So today's topic is stochastic differential game with 2 players and impulse controls. So welcome, Professor Campi.
Thank you. Thank you very much for the invitation. So I will be talking about this joint project with René Aïd. He was formerly at EDF, now he's in Paris Dauphine. Matteo Basei was actually PhD students in Padova, now it's in Berkeley for a postdoc. Giorgia Calegaro and Tiziano Vargiolo, they are both in Padua University Math Department. And this is a project on non-zero-sum differential games with impulse controls. And in particular, this is a verification theorem-based approach, in a sense that our aim is to have like a tool in order also to be able to give explicit solutions for the problem we are interested in. So this is the outline of the talk. So I will, here, I will give the definition, I will define the setting of the problem of this non-zero-sum impulse games. And actually, before the general setting, I will also be talking about some motivating example, which has like a couple of possible financial interpretations, but I will not be spending too much time on the interpretations. Actually, it's just half of a slide actually, this. And then actually the rest of the talk is really focused on the theoretical aspects of the problem. And then we have this verification theorem here. So saying in a nutshell that actually under some regularity assumptions, you can characterize the value functions of the 2 players as solutions of some system of quasi-variational inequalities, okay? And so if you're able to solve the system, if the solution is regular enough, that actually you get the value function, and also you get a way to compute explicitly the optimal strategies of the players. Then I will come back to the motivating, actually, example of the beginning, and I will show you that actually within this example you can really compute everything. Okay, so everything is explicit. You can compute all the parameters. You have the shape of the 2 regions, intervention and intervention regions for both players, and so on. So you can really characterize completely the example here, and then I will conclude. Okay. Okay, right. So just to start with an example. Which actually motivated us. We consider 2 players, player 1 and player 2. We have one-dimensional state variable, x, living in a real line. And the 2 players have opposite goals. By this, I do not mean that actually it's a zero-sum game. The game is still non-zero-sum. Just the goals are opposite, but doesn't necessarily mean that actually the gains of the 2 players sum up to 0, okay? Let's say that the state variable x, when no one is actually doing anything, so when no one is intervening, it's just a Brownian motion with some initial condition small x and scaled with some volatility coefficient sigma. Okay, so very simple state variable. What happens when actually player 1, for example, before saying this, actually I should say something at least roughly about the objectives of the 2 players. So I will be more specific later, but let's say that here for the moment, player 1 likes high values for x, while actually player 2 is the opposite, so he prefers when actually the state variable is low, okay? And the players can shift the process x, so they can actually shift it. Let's imagine that x is the current value of the state variable, so actually player 1 as well as player 2, they could actually shift it, so turn the current value to a new value, x plus delta, and delta is the impulse which is chosen by the players, okay? Actually, the players choose the time of the intervention and the size of the intervention, okay? So every time one player intervenes, he or she pays some cost. This actually, there is a consequence of this, is that since every time the players intervene, they have to pay a cost. Of course, they don't want to intervene all the time, okay? So it's, they will do it from time to time, so they will be choosing a sequence of stopping times, and along those sequences, they will be actually applying those impulses, okay? So they pay some cost, And the cost in the example, as well as in the general theory, you will have like two components, a fixed cost and a proportional cost. Proportional, I mean proportional with respect to the size of the intervention, okay? And then here we are interested in computing Nash equilibria as explicitly as possible, okay? So the approach is kind of a standard one in controls, the theory, as well as in differential games. So you try to find a verification theorem, which has like some assumptions, some regularity assumptions, not too binding, in a sense that, of course, you would like to find examples satisfying those assumptions, okay? So we look at computing Nash equilibria as explicitly as possible, and here, actually, this is the only bit talking about financial interpretation of this setting here. You can think of two possible interpretations here. So, for example, imagine that the two players are the two central banks of two different countries, and the state variable is an exchange rate between their currencies. So, of course, depending on how actually the exchange rate is computed, I mean, I don't know, let's say exchange rate is like the currency of of the country one divided by the currency of country two. So, of course, one of the two central banks would like this exchange rate to be very high, the other one would like to be very low, okay? So they have two opposite goals, but of course they do not necessarily sum to zero, okay? So it's not a non-zero, it's not a zero-sum game. Another interpretation here is that X being, for example, the forward price of energy, of electricity, okay? One player, let's say player one, could be an energy producer, okay? So he has the possibility of increasing or decreasing the price with impulses, because of course, he doesn't want to change it all the time, because otherwise consumers will not be happy. And the player two, for example, player two can be like an energy consumer, but a big one, okay, in the sense that could also have an effect on prices, okay, by some reason. I mean, through many ways. Actually, this big consumer can have an effect on the prices, right? Yeah, of electricity. Okay, so these are the two possible interpretations that you can give to this problem, but of course there are many more. I mean, this is a very general setting. Okay, this is just a motivating example, but you will see that the setting is more general. Okay. Okay, right. So just to be more specific about the processes involved here. So again, this unaffected state variable, which is a state variable when no one intervenes, is given by this guy here. So initial condition plus some Brownian motion, rescaled by some volatility sigma. Strategy for player I, as I told you before, is a sequence of two things. You have a sequence of stopping times, tau ik, so those are the intervention times of player I, and the other sequence is delta ik, which is a sequence of the sizes of the impulses, okay? So at each intervention times there is this impulse here, and the impulse is a random variable, which is measurable with respect to the sigma field generated by the state variable up to time tau ik, okay? And after interventions, you can define the state variable as follows. So you have, of course, you have xt, which depends on the initial condition, or it depends on the two strategies, u1 and u2. And it is given by this component, which is just the unaffected part, plus the shifts, the accumulated shift coming from player one, and accumulated shifts coming from player two, okay? And also, as I told you, we have costs, so we have a fixed cost C every time that actually player I intervenes. And you could also think of situation when actually every time player I intervenes, okay, he has to pay a cost, but he's also like inducing a gain for the competitor, okay? So there could be a corresponding gain C tilde for PJ, okay? You could also have like some proportional cost, a cost which is proportional to the size of the intervention, with also like a corresponding gain for the opponent, okay? And here in this motivating example, we assume that the running payoffs, because here the players are maximizing, running payoffs are linear, okay, linear in the state. Here you have two more parameters, S1 and S2. They are a kind of thresholds that are actually fixed from the outset for the two players. In a sense that, as I told you, here is, for example, let's look at player one. So player one, actually, he's happy when X is very high. So at least higher than S1, okay? While player 2 is happy when actually X is low, so lower than S2, okay? And of course, is very happy when actually X is very low here, okay? So they have actually two opposite goals here. But of course, F1 plus F2 is not necessarily equal to 0, okay? And here we are assuming that S1, the threshold for player 1, is actually strictly smaller than the threshold for player 2, okay? So this is the example you will see at the end of the talk. We'll be able to say actually everything about this, about the solutions and about the value functions and also about the optimal strategies, okay? Okay, right, so what are the objectives of the two players? Because I didn't tell you anything about the objective functions of the two players. So here, what do you have? Player I, for example, he wants to maximize this guy here. Okay, so you have expectation of running reward. So it's an infinite horizon problem. So it goes from 0 to plus infinity. You have a discount factor, exponential minus rho t, times some running cost, fi. Fi is the functions of the previous slide. Then you have this, the cumulated costs. These are the cumulated costs due to intervention of player I. And these are the cumulated gains coming from interventions of the competitor. Okay? And in both costs, actually, this is a cost, this is a gain. But again, I mean, cost or gain, it really depends on the sign of these guys here. And so far, I didn't assume anything about the signs. But anyway, this is usually it's a cost here. And these are the costs paid by the player only in case of intervention. These are the gains that player I gets in case of intervention of the other player. Okay. So actually, this can be described as a two-player non-zero-sum game with impulse controls. Okay. And there is not much actually in. We were actually pretty surprised, but there is not much in the literature about this kind of game. So here is just some very little review on the literature. I'm just quoting only the papers which were really relevant for us, but of course, I mean, literature is much longer. So here we have this, table here. So you have stop-in time or impulse control. Actually, impulse control is more general than just stop-in time here, stop-in time game. And here we distinguish between zero-sum game and non-zero-sum game. Okay, so here, for example, for a zero-sum stopping game, the most influential paper is the one by Friedman here, so Friedman 73. And in this case, the players choose tau 1, tau 2, so as to maximize. So the first player maximizes this guy here, the second player minimizes it. Okay? And the structure of this reward is kind of similar. So you have a running reward here, discounted, and then you have some final reward. Okay? Reward that actually player 1 gets at time of when actually the game stops. Okay? Or you have also this other paper by Bansusan and Friedman 77, when actually still the control is just a stopping time, but actually the game is a non-zero sum. Okay? So in this case, player 1, for example, player I wants to maximize this guy here. So you can see the reward are indexed by I. Even a discount rate here is indexed by I, okay? So really, I mean, this is not necessarily a zero-sum game, of course, but otherwise the structure of this reward is the same as before, okay? There are also more recent paper, actually, there is very, very nice paper by Giorgio Ferrari, Tiziano De Angelis, and John Moriarty here that I think is forthcoming in Annals of Applied Probability, where actually they have explicit characterization of the optimal strategies of the two players within the class of threshold type strategy. So a threshold type strategy is a strategy where basically when a set variable reaches a given threshold or actually goes above or below, it depends if it's a maximization or minimization. But let's say when the set variable goes above a certain threshold, then in this case, player 1, let's say, decides to stop. Okay, so this is this kind of strategy which is called threshold type, and they give complete characterization of Nash equilibrium for this type of strategy. Okay, in a very general model. Okay, here in this part of the table we have two-player zero-sum game when actually the control is an impulse type control, and we have this paper by Andrea Cosso. And in this paper also is very general, and what he proved is that the value function of the game, in this case, is only one function because the game is zero-sum, okay? So the value function of the second player would be like minus the value function of the second one. So in this case, the value function is actually unique, I think possibly discontinuous viscosity solution of a system of a quasi-variational inequality, okay? In this case. And so the control is an impulse controls, and players that wants to maximize, let's say player 1 wants to maximize this guy here. So it's very similar as the reward functions that I showed you before, okay? But actually here, we were surprised, but actually we couldn't find anything for this case, okay? So it's a case of a non-zero-sum impulse game, okay? So actually that's why we decided actually to see if something could be done, okay? Right, so actually our goal here is kind of trying to fill this gap here. So we want to, first of all, to give a rigorous formalization of the problem, okay? And especially, I mean, the definition of the control state variable is not actually trivial here, because you could have accumulation of interventions, you could have simultaneous interventions, so it's not necessarily like a trivial problem. So anyway, you have to realize at some point that you cannot consider really all possible strategies here. Otherwise, the state variable, the control state variable is clearly not well defined, okay? Then we have a verification theorem here. Verification theorem telling you that actually if the value functions are smooth enough, then actually there are solutions to some system of quasi-variational inequality. And then, of course, another important part is, I mean, just to give validity to this theorem here, it's try to be able to find actually examples where actually the verification theorem can be used, and can be used actually in order to find explicit Nash equilibria, okay? So this was actually our goal. So just let me give you a short, brief, actually, description of the general model. So the general game, you have, first of all, you have two players. The players is like before, so the players can affect a given state variable. The state variable can be taken more general than before. So it's some solutions, unique strong solution of some stochastic differential equation. The players intervene with discrete time interventions, so impulse controls like before, so they can choose the sequence of times of intervention, the sequence of sizes of the intervention. Now, the effect that their interventions have on the state variable is not necessarily of an additive type, actually. So it can be a shift, like in the motivating example, but it could also be something general, okay, more general. Just they could actually turn the current value from x to some function of x and of the impulses, not necessarily additive function. And player I wants to, like before, he wants to maximize the following payoff, same structure, just that here the costs are more general, not necessarily fixed cost plus proportional cost. So here let's look at the first part. So you have the running reward. So it's an integral from 0 to tau s. So even here, it's not necessarily finite horizon. Tau s is the exit time from a given domain S, okay? Discount factor, the discount rate could depend on the player, okay, rho I. Running reward, just a function fi of the state. Here you have cost. So this is the cost that actually player I pays every time he or she intervenes. And it's just a discounted function, phi of I, of the state. This is the state tau ik minus, so it's just a state immediately before the intervention, and the size of the intervention. Okay, now this is actually what he gets from intervention of the competitor. And then, of course, here you have an exit. So the problem could be, the game could stop in a finite time. So you could have actually a reward when the game stops, okay? So some function h of the value of the state just before the game stops, all right? Only when, of course, only when the game stops in a finite time, okay? Otherwise, it's just 0, okay? And, okay, of course, we look for a Nash equilibrium of this, for this game. Okay, right, so now let me give you just the rigorous now formulation of the model, okay? So you have an unaffected state variable like before, which now I call y, okay, instead of x, just to increase the entropy of the, the top, no reason. So dy is just unique strong solution of this stochastic differential equation, so homogeneous, because in case the horizon is infinite, actually we want to have time homogeneous problems, so we want to deal with ordinary differential equations instead of PD and so on, okay? So we have this unaffected state variable here. So now every player can exert some control. The controls are impulse controls, so they are sequences of intervention time. So tau ik, mathematically speaking, is an increasing sequence of stopping times. So here, of course, I didn't specify, but of course there is a probability space in the background, omega fp, with a given filtration, could be the filtration generated by the Brownian motion, could be something bigger, okay? But of course then, if it's something bigger, W has to be a Brownian motion with respect to the filtration, which is given from the outset, okay? So this is an increasing sequence of stopping times with respect to the given filtration. And delta ik are random variables, so they are just elements in L0, so the space of random variables with finite values, measurable with respect to f tau ik, okay? So basically the player decides when to intervene and then decide also the size of the intervention on the basis of the information he accumulates up to that point in time. Okay. What is the effect of the impulses? So when player I intervenes with some impulse delta, when actually the process shifts from y to some function of y and of the intervention delta. Okay, not necessarily y plus delta, could be something more general. Okay, and this gamma I is a function that depends on the player. Okay, continuous function. Okay, right. So now, for tractability here, because actually, I mean, after all, we are interested in getting like explicit solutions for the game. Okay, at least to be able to characterize explicitly one Nash equilibrium. So we have to focus on some strategies that we can work with. Okay, in the application. So what we do actually, we focus on this kind of strategies. So. We say actually that the strategy for one of the two players, player I, is a couple of two things. So we have AI and xi. So AI is a given subset of the state space, and xi is some function from the state space to itself. Okay. So what are the roles of these two guys here? So this strategy is actually works as follows. It's a kind of a recipe for the player I. So imagine the player I decides to use this strategy here. Okay. So what it means that he keeps track of the state variable. When the state variable hits the boundary of this set, AI, then actually he decides to intervene, and he decides to apply this impulse, xi. Okay? But AI, I mean, it's not fixed. I mean, it's not given to the player. It's part of the strategy, so the player can decide actually when, which kind of set AI he wants to use. Okay? Right, so any pair phi I and any starting point for the state variable, they uniquely determine a pair of impulse controls and some control process as well. Okay, and it works as follows, exactly what I told you. So player I intervenes if and only if the process hits the boundary of the set AI. Okay, and in this case, he applies some impulse, which is given by the second element of this pair. Okay. And here again, because it's really very delicate here how, in case of simultaneous interventions, how you would define, it's just not even clear in case of simultaneous intervention how you could define the control state variable actually. So here we decided to adopt this convention. In case of simultaneous intervention, we say the player one has a priority. Okay, because otherwise it's really complicated to define it. Because here the way you can define actually state variable in this case is just you can define it like piecewise. So state variable is basically a Brownian motion if no one intervenes. So it just evolves like a Brownian motion up to the first intervention time. So let's say player one intervenes. Okay, then the state variable is shifted. Okay, and then this also you can define this as a jump in the dynamic of the control state variable. And then, okay, after the intervention, again, it's a Brownian motion, so it continues. And then you have player two intervening, okay? So there is another jump in the dynamics of X, and so on, okay? But if there is simultaneous intervention, it's not clear, actually, how you could define, what do you do to define the control state variable, okay? So this is the convention we decided to take here. Okay, right, so this is exactly what I told you. So intervention times can be ordered okay? And so the control process can be defined in a recursive way, okay? Like the way I describe it. Okay, so we can define a control process now. So given strategies, okay? So UI x phi 1, phi 2 is the sequence of intervention times and impulses. We can define a control state variable, which depends on the state, on the initial state, depends on the two strategies, phi 1 and phi 2, okay? And now what happens at the end of the game? So the game ends when x exits from some fixed subset S, okay? S is given, some domain, and tau S is the first exit time from that domain, okay? And then we have a final cost, HI. We also have intervention costs and gains like before, okay? So I'm going to be very fast on this. And then also we have some running payoff f of I, and which is discounted by some discount rate, which is rho I, so it could also depend on the player, okay? Right, so actually this is what the two players want to maximize, okay? So player I wants to maximize this guy here. So again, this is a running payoff. This is the cost coming from his intervention. This is the cost or gain coming from the competitor's interventions, and this is the final gain. Okay, right. There are some technical assumptions again about the strategies. Okay, so now we want to define a set of admissible strategies within which actually we will be looking for the Nash equilibrium. Okay, so here I'm not giving you the precise formulation of this, but what do we have? We have some integrability for the control payoffs, because of course we want this guy to be finite. Okay, so we have to assume some integrability conditions of f on phi, on psi, on h. Okay, right. So this goes into the definition of admissible strategies. Okay, so the players can use only those strategies making this guy finite. Okay, so this is the first thing here. The second, again, we want to avoid another kind of degenerate situation. Okay, so the first degenerate situation is the case of simultaneous intervention. All right, so the other one is accumulation of those intervention times. This is also something that we want to avoid. Okay, so this goes in again into the definition of admissibility. So we're just assuming that actually the players are not allowed to accumulate intervention times. Okay, this is also very classical assumptions in impulse control, even without the game part. This is something that which is usually assumed, because otherwise it's complicated, because if they accumulate, then you have to deal with explosion, possible explosion of the diffusion. So okay, so and the solutions that you want to focus on is actually solutions which are actually viable. So solutions, sequences of interventions that do not actually let the process to blow up. Okay. Okay, right. And we are interested in Nash equilibrium, so this is the usual definition of Nash equilibrium. Okay, so it's basically a situation. So it's a couple of strategies, phi 1 star, phi 2 star. So it's a place basically from where no players wants to deviate from. Okay, unilaterally. Okay, so which means, for example, for player 1, if player 1 decides to deviate here, well, his expected profit will decrease, okay? If the second player doesn't change his strategy, okay? And the same for the second player here. So this is important that actually the deviation are considered only within the class of admissible strategies here, okay? Okay, so this is the definition we are interested in. So we define the value functions then. So if phi 1 star, phi 2 star is a Nash equilibrium, then actually the level of profit, of expected profit that they can achieve by pursuing these two strategies, player 1 is given by V1, for player 2 is given by V2, and they are called value functions. Okay? Okay, right, so this is our goal. And now we want to, okay, so now what we want to do is basically we want to get the good system of quasi-variational inequalities for the value functions. Okay, so this system will characterize value functions in the sense that if you are able to solve the system, then you get the value functions. And then actually, if you know the value functions, it's very easy then to get the optimal strategies for the players. Okay, so I will give you just some heuristics first, which explain actually why you should why it's natural to consider exactly the system I'm going to have actually in the verification theorem. And okay, so let's assume for the moment that okay, v1 and v2 are the value functions, and let's assume for the moment that gamma 1 is just an additive function. Okay, so we are just dealing with additive shifts. Okay, like in the motivating example, right? So assume now that you know the value functions. Okay, so you know the value function. Of course, value function will be solutions of this system. Okay, but let's assume that you know them for the moment, and then you want to find the optimal strategies. Okay, assume also that there exists some delta I, some impulse, one impulse, realizing the maximum of this guy. Okay, what is this guy? Well, vi is the value function evaluated at the state variable after the impulse, so x plus delta. And then this is the cost that you are paying for the impulse. Okay, and then you maximize with respect to all possible delta, all possible impulse here. Okay, so basically delta is the optimal impulse if you want to intervene immediately. Okay, so imagine that the state now is small x. You decide that you want to intervene. What is the optimal intervention size? Well, it's given by the solution to this static optimization problem, which you can solve very easily if you know vi, of course. Okay, right. Now let me introduce these two notations here because they will be very important in the next slide. So these are two operators, script mi and hi here. So what is this? So mi basically is describing the effect of immediate intervention of player I on his or her value function. So player I decides to intervene immediately. He applies this impulse delta I. This is the effect of the impulse on his value function. Okay? This operator here, hi, is describing the effect, again, on the value function of player I, but due to the intervention of the other player. Okay? So this is why we have to distinguish these two effects, okay? Still effects on the value function of player I. The first one is coming from itself. The second one is coming from the competitor, okay? Right. Okay, so interpretation of these quantities, just like before, vi is the value of the game for player I. This guy is the value of the game for player I in case of immediate intervention, right? Because the state shifted from x to x plus delta plus the cost, okay? Delta I is the optimal impulse that player I can apply, okay? And MIVI is the value of the game for player I in case of immediate optimal intervention by himself or herself, while actually HIVI is the same guy, but actually in case of intervention of the competitor, okay? Right. So now, this is the main, this is a guess actually how things should behave here in this setting. So it is natural to argue that the Nash policy should be the following. So here we are still assuming that we know the value function, okay? But if you know the value function, we can argue as follows. So player I intervenes only if MIVI is equal to VI, okay? Because when they are equal, it means that actually intervening immediately is optimal because you get something which is equal to the value function, which is the maximal thing that you can get, okay? So player I intervenes only if you have this equality here. And the optimal shift is equal exactly to the delta I, which is a solution to the static optimization problem that I showed you before. Okay? So if you know VI, you know exactly what to do here. Okay? Now, of course, the problem, if you want to, you need to find VI in order to complete the description of this strategy, right? So just some heuristics here. So now we want to get the system of quasi-variational inequality for VI. Okay, so first, this is easy, right? So when the state variable is the boundary of the domain, then of course VI is the value function that must be equal to the final reward, okay? Now, what is this? Well, again, this is something which is natural to expect. So we expect this guy to be lower than 0. Why? Because, well, Vj is the value of the game for player j, so this is the maximal actually expected profit that he can get, and this must be bigger than this guy, which is actually the value of the game for player j in case of immediate intervention. Okay, this is negative in S. All right. Now this is actually kind of the new part here that you don't have usually. You don't have in a zero-sum game. So what happens in this region here? So this is the region where player J intervenes. You remember, because when this guy is equal to this guy, it means that actually for player J, it's optimal to intervene immediately, right? So player J intervenes. So what happens to player I in this case? Well, in this case, since we are looking for equilibrium, player I cannot lose anything by intervention of player J, because otherwise for him it would be optimal to deviate, okay? So it's natural to expect that actually when player J intervenes, well, in this case, player I does not lose anything, which means that actually the intervention of player J has no effect on the value of the game for the other player, okay? And then what happens actually in the other half of the space? Well, if mj vj minus vj is strictly less than 0, so in this case, player J does not intervene. Okay, but if player J does not intervene, for player I, it's like a usual control problem, okay? So usual control problem with impulse controls, and you know that for impulse controls, this is actually the equation, this is actually the variational inequality that the value function satisfies, okay? It's the maximum between this guy, now this guy is just the PD, actually in this case is an ODE describing the value functions of player I. A here is the infinitesimal generator of the state variable, okay? So which means that basically the maximum must be equal to 0, right? So which means that both guys here are non-positive. Now, when this guy is equal to 0, okay, it means that player I is intervening, okay? But when this guy is strictly negative, the other guy has to be equal to 0, which means that the process is just evolving by itself on its own, okay, without any intervention of player I, right? So these are actually the equations that you would expect here. This is exactly what you have in the verification theorem. So what you have here, you assume that, okay, that V1, V2 are functions from S to R, so S is a state variable. They satisfy some weak technical assumptions, but actually the most important technical assumptions are here. There are a couple that are not mentioned here, but actually one is that the domain has to be smooth enough, the boundary of the domain S. So in particular, we assume that the boundary of the domain is the graph of some Lipschitz function, for example, and then it works. And also we need to have some local boundedness of the derivative of Vi at the boundary of the domain again, okay? So I didn't put the assumptions regarding what happens at the boundary of the domain, but anyway, I mean, the examples that we have, they are all satisfied. So apart from those assumptions, these are actually the most important ones. So V1 is a classical solution to the system, the previous system. And then they have to be smooth enough in this sense, okay? So C2 in dj less the boundary of the I. So actually the I is the non-intervention region, okay? Has to be C1 in dj and has to be C continuous in the whole domain, okay? And polynomial growth, of course, because we need like some estimates, because here, of course, if you can imagine that the proof is really based on application of Ito's formula. In Ito's formula, you have some local martingale part, and if you want to prove that the local martingale part are true martingale, you need some estimates, okay? So, right, so if you are able to exhibit these two functions, V1, V2, satisfying those assumptions, then actually you can also find the optimal strategies in the way I showed you before, okay? So phi I star is given by this couple here, so the I delta I, and the I is exactly this region. You see, it's the non-intervention region, so as soon as the state variable is in the I, you don't do anything. When actually the state variable hits the boundary of the I, which means that this guy is actually an equality here, so it's the right moment to intervene. The intervention size is given by this delta I here, which is exactly the solution to the static optimization problem of the previous slide, okay? And assume, of course, that this guy is admissible, so it satisfies all the admissibility conditions that we put on the strategies, then you can claim that actually this couple here is a Nash equilibrium for the game, okay? And this is the way actually you will be using the theorem in the application. So imagine again you are able to find solutions to this system of quasi-variational inequalities. Then what do you get? You get that player I intervenes only if X exits from this region, okay? And when intervening, player I shifts x from the current state, so to the state x for delta I. Okay, so this is in the application, so where actually the shift is additive, where delta I is the unique maximizer of this problem here, of this function. Okay, right. Okay, so of course now the difficult part here in the example, if you want to use this verification theorem, is first you need to solve the system of quasi-variational inequalities, which is actually not necessarily an easy task. It depends on the example, of course. Okay, so let's see what happens in the motivated example. Actually, here it's we can compute everything explicitly, also because the example has a lot of symmetry, symmetry. So actually, what you compute for the player I somehow can be also used to compute strategies for player 2. So you save time, okay, from this point of view. Okay. So let's go back to the example, to the one-dimensional game. Again, I mean, just to remind you briefly, what is this about? So we have player I shifting the process x, while paying or getting some fixed cost or proportional cost. This is the functions that player I wants to maximize, okay? Where, okay, again, running reward, cost of intervention, costs, again, coming from intervention of the other player. The running reward are linear, okay, in the state. And this is the controlled state variable. So as you can see, now the shift is additive. So actually, the state variable is just given by the unaffected state variable plus the accumulated shifts coming from the two players. Okay. We assume something now about the cost. Okay. So we are assuming that C is bigger than C tilde. So C is the cost that player 1 is paying, and C tilde is the gain that actually he's getting from intervention of the competitor. Okay, and also we assume that lambda is bigger than lambda tilde, and we assume that actually we don't have equality everywhere here, because if this happens, okay, we'll say a few words in the end, but if this happens, we are in some degenerate situation where actually you can have simultaneous interventions all the time. Okay, so we exclude this case by just assuming this condition here, and lambda rho has to be strictly smaller than 1. Okay. Okay, right. So this game, of course, it's a particular example of the general setting. Okay, so we can try to apply the verification theorem here. Okay. Okay, right. So let's see. Let's look for candidates first, right? So I will call V1 tilde, V2 tilde the candidate value functions. Okay. So we are trying to use quasi-variational inequality problem in order to find a good candidate. Okay. So what do we have? So we take this function here as a candidate. So vi tilde x is given by these three guys here. So in this region, this is the region where player I intervenes. Well, if he intervenes, actually the value of the game for him is just given by mi vi tilde. Okay, is what happens actually in case of immediate intervention. Okay. In this region here, which is the region where no one is intervening. Okay, well, in this case, the state variable is just evolving like a Brownian motion with some volatility sigma. Okay, so the reward of the two players is just expectation of the running reward. There are no costs because no one is doing anything here. And so you just have this expectation. You can use Feynman cuts. You have a PDE. Okay, in this case, it's an ODE. Okay, because the problem is time homogeneous. So actually, the value of the game in this case is just the function phi. Phi is a solution to this equation. Okay, the usual equation that you get. Okay, in Feynman-Cast representation, where A here, script A, is the infinitesimal generator for this the unaffected state variable. Okay. In this region, which is the region where player J intervenes, well, in this case, what happens to the value of the game for player I? Well, this is just, you get hi vi tilde, okay? So this is, I didn't do anything here. I'm just using the definition of mi, hi, and the fact that when the process is unaffected, where this is just Feynman-Cast representation, okay? Right, so now phi is, of course, you can solve this equation explicitly up to some parameters. It's the usual thing here. So this is just a linear combination of exponential functions plus this term coming from the reward, the running reward here. And theta is square root of 2 rho divided by sigma squared. And these parameters, of course, they have to be determined because I don't have any boundary condition here. Okay, so A11, A12, so we have 4 parameters, okay, to be determined. Right, so what about intervention regions? Of course, we need to also make an ansatz on the shape of the intervention regions at some point. So now this part is, again, this is a heuristic part, but since the goals of the 2 players are kind of opposite, and are actually very simple, because player 1 is very happy when x is very much above S1, for example, okay? So we can imagine that his intervention region is of this type. It's minus infinity x1 bar, okay? So in a sense that the player 1, what does he do? Well, he has his own personal threshold that he can tolerate, in a sense that if the process is higher than x1 bar, he's happy. He doesn't do anything, okay? But when actually the process is below x1 bar, for him is actually too low, okay? So he decides to do something. He applies an impulse, okay? Of course, this x1 bar is determined at the equilibrium. So this is an additional parameter that has to be determined, okay? But at least we have an ansatz about the shape of the intervention region, okay? Which is very simple. It's just this half line, okay? And symmetrically, since the other guy is also like has an opposite goal, but he likes when the process is very low, well, actually in this case, he also will have like his own personal threshold. When the process is like below x2 bar, he's happy. When it's above, well, he's not happy, so he will apply an impulse, okay? So this is exactly what happens, right? And since the 2 thresholds are ordered in this way, we also expect that the same order will be also true for the personal threshold that will be actually determined at the equilibrium, okay? Right, so what do we have? Intervention region for player 1 is this half line here, minus infinity x1 bar. The non-intervention region, of course, is this open segment here, x1 bar, x2 bar, where actually when the process is, I mean, everybody's happy because it is high for player 1, it is also low for player 2, so actually it's fine for them. And player 2 intervenes when actually the process is too far above x2 bar, okay? Okay, right, so let's inject all this in our ansatz, okay, for the value functions. So we have that v1 tilde, for example, is given by this guy, m1 v1 tilde in the intervention region, okay? In a non-intervention region for both players, it's just this function phi 1. In the intervention region for player 2 is just h1 v1 tilde. And okay, the same for player 2, right? Okay. So now we know phi I up to some parameters, but now we have to compute these 2 guys here, mi and hi, okay? And of course, I mean, we still have to determine the personal threshold of the 2 players here, okay? Okay, right, so, but now for m1, h1, I mean, it's not so difficult because they are just a static optimization problem, okay? So for example, m1 v1 tilde is given by this optimization problem here. So it's the supremum over all deltas. And actually you can restrict to positive deltas because the negative deltas are clearly not optimal for him. So delta positive, v1 tilde x plus delta minus the cost, the fixed cost minus the proportional cost, okay? You can do change of variable, you can reduce to this equivalent problem here, okay? You do the same for player 2. And assume, actually this is something that will have to be verified, but let's assume for the moment that you have a unique maximizers for all these optimization problems. And they belongs in this interval here, because of course they would apply an impulse, so they want to push the process in a zone where actually they are happy, okay? So they will be actually pushing the process X towards some point, some target point, x1 bar, for example, for player 1, which is in the region where actually player 1 is happy, will not intervening, okay? So it will be actually pushing process X to x1 star, which is somewhere in the non-intervention region, and the same for player 2. Player 2 is just looking at the state variable is too high for him, then he applies an impulse, and impulse is actually bringing the process X to some target value, which is, again, in the non-intervention region, okay? Right? And these are just the first order conditions coming from solutions of these optimization problems, okay? Right. And okay, and then in this case, if we are able to find those maximizers, well, M1 V1 tilde is going to be equal simply to this guy. So phi I at the optimum minus the fixed cost minus the proportional cost. Okay, and the same for the other three guys here. Okay. Okay, right. So now we have all these parameters. Actually, we have the 4 parameters in phi I. Okay, A11, A12, A21, A22. We have the 2 personal threshold, x1 bar, x2 bar, and now we have the 2 optimal targets. Okay, x1 star, x2 star. Okay. So these are all parameters that have to be determined. And so we have to add actually some equations, okay, in order to be able to find the values for those parameters. Okay, so now we're going to be using these regularity conditions of the value functions on the intervention and non-intervention regions. Okay, and so we use the smooth pasting conditions, as they are called, and then we get equations that will allow us actually to determine the parameters. Okay, so V1 tilde, V2 tilde are smooth in this region here. Okay, so we have to set the parameters so that Vi tilde, for example, is continuous at the boundary of intervention region of player 1, at the boundary of intervention region of player 2, and Vi is differentiable at the boundary of player I intervention regions. It doesn't have to be differentiable at the boundary of the other player intervention regions. Okay. And these two conditions actually will give us smooth pasting conditions, so more equations for our parameters. Okay? Okay, right. So this is what we have so far. So for example, this is the value of the game for player 1. So in case of intervention of player 1, the value of the game is just phi 1 minus the fixed cost minus the proportional cost. In case of non-intervention, it's just phi 1. In case of intervention of player 2, well, it's just phi 1 at the optimum of player 2 plus the gain coming from intervention of player 2. Okay? And symmetrically, the same thing for player 2 here, right? Okay, so now we have these 8 parameters. Okay? The first 4 parameters, they appear in phi 1 and phi 2. These are the 2 personal threshold, okay? And these are the 2 optimal targets for the 2 players, right? And they have to satisfy somehow in our answers, or at least in the equilibria we want to compute, they satisfy these 2 order conditions. Okay, the 2 targets, both optimal targets, lie in the non-intervention regions for both players. Okay? Okay, right. So these are all the equations that we have. Okay? So the first 4 equations, they come from optimization problem for the of player 1. Okay? The last 4 from player 2, right? And so it's good, I mean, at least because you have 8 equations and 8 parameters, so at least the numbers match. Okay, but actually now we have these theoretical results proving that there exists a unique atyple of parameters satisfying the previous conditions. And okay, so this is some technical conditions, but okay, now it's not actually necessary to comment on this. And the main idea of the proof is really that the game basically is symmetric. It's symmetric around the midpoint between these 2 thresholds, S1 and S2. Okay, so everything is symmetric around this point, basically. Okay, so the value of the games is also symmetric. So actually, what happens is that all these couples here, the 2 personal threshold, the 2 optimal target, the functions phi 1 and phi 2 are also actually symmetric around this point. So actually, the nice thing is that you can decouple the system here. Which here is not clear that you can do it, but actually you can decouple the system. So you can have 2 complete separate systems, one for player 1 and one for player 2, okay? And you can solve them separately. Actually, you can solve the first one. The second one is just you deduce it from the first one by symmetry, okay? So you just have 4 parameters and 4 equations to determine, basically. So you can solve everything explicitly here, okay? So this is the formula that you get here. Okay, so this is the formula for the personal threshold of player I. This is the formula for the optimal target. This is the formula for the parameters appearing in these functions, phi 1 and phi 2. Everything can be expressed in terms of all the parameters of the model here. Only one parameter has to be computed numerically, this guy here, the parameter xi, belonging in this interval 0 eta, is a unique zero of this function here. Okay, but it's just some nonlinear equation that it needs to be solved numerically. This can be done, okay? But the other parameters are explicitly expressible in terms of the initial data of the problem of the game, okay? Okay, right. So just some final observations. So the system of quasi-variational inequality actually have more than one solution, okay? But only one satisfies the order condition that actually we imposed, okay, on the threshold and on the targets. Even the values of the game are actually symmetric around this midpoint, S tilde, okay? And this is the thing that I anticipated before. So what happens when actually the structure of the costs is such that C lambda is equal to C tilde, lambda tilde here, where in this case, this parameter gamma appearing before is 0. So gamma is this parameter here, appearing everywhere, actually. And well, in this case, this is a really completely degenerate situation where actually players intervene infinitely often at each instant. Okay, so this is really a situation that really we want to avoid. Okay, or I mean, this equilibrium is not really very interesting anyway. Okay. Okay, so just to conclude, so what we did, so we considered some non-zero-sum impulse games. You can find many applications. Okay, here I just showed you a couple of interpretations in terms of control of exchange rate, in terms of some game between an energy producer and some big consumer of electricity. The state variable is pretty general. It's just a solution of some SD. Also, the structure of the reward or the cost is actually pretty general. We have a verification theorem. Now, the verification theorem, of course, is the merit of identifying actually the good system of quasi-variational inequalities under some regularity assumptions. Now, these regularity assumptions can be too strong for certain applications, but at least not for the examples I showed you. But yeah, I mean, maybe for some application, they could be not very easy to use this verification theorem. So actually, one possibility, one goal for the future could be actually trying to weaken the conditions, okay, of that theorem. And but also another actually possibility could be really to characterize the value of the games as viscosity solution of this quasi-variational inequality, so that actually at least you can try to use numerical methods on the quasi-variational inequalities that actually allow to compute numerically the value function. And then if you know the value function, actually it's easy to get the optimal strategies from there, okay? The main problem is actually to compute the value function and so to have an idea of the shape of the intervention and non-intervention regions, actually, okay? So this is the verification part, and then we have examples. This is also something that is not very easy actually to find usually for this type of games. So we have this example where actually we really exploited heavily the symmetry in order to get explicit solutions for the intervention, non-intervention region, as well as for the optimal impulses. And in the paper, which is actually available on arXiv, you can also check. We also study some limit case, like when the cost is very small or when the cost actually is very high here. And also we provided now actually in the last version, we provide some non-symmetric example, okay, where still you can apply the verification theorem. You are not able to solve explicitly, to compute explicitly the parameters. You have a system of algebraic equations, but that you can solve numerically, actually, okay? And, okay, so that's it. I can stop here. Thank you.